properties based on dual nature of radiation. The radiation of light shows a dual nature, that is wave and particle. Phenomenon like diffraction, interference and polarization can be explained on the basis of wave nature of light, whereas phenomenon as like photoelectric effect, Compton effect, etc. can be explained only in terms of quantum theory of light. Quantum theory of light states that light is a composition of small packets called photons and have wavelength properties. Photoelectric effect. In 1887, H. Hertz performed a very interesting experiment in which electrons, that is electric current, were ejected when certain metals, for example potassium, rubidium, cesium, etc., were exposed to a beam of light. This phenomenon is called photoelectric effect. The following important observations have been made in the study of photoelectric effect. 1. Rate of emission of photoelectrons from a metal surface or photoelectric current is directly proportional to the intensity of incident radiation. That is, the number of electrons ejected is proportional to the intensity or brightness of light. And 2. Emission of photoelectrons starts as soon as light falls on the surface of the metal. It has been found that the time lag between the incident of light and emission of electrons is less than 10 to the power of minus 8 second, which is negligible. Third, the emission of photoelectrons takes place only when the frequency of the incident radiation is above a critical value. That is, for each metal there is a characteristic minimum frequency, nu naught, also known as threshold frequency, below which photoelectric effect is not observed. The threshold frequencies of some of the metals are cesium 4.8 into 10 to the power of 14 Hz, potassium 5.8 into 10 to the power of 14 Hz, magnesium 9.0 into 10 to the power of 14 Hz, zinc 10.7 into 10 to the power of 14 Hz, nickel 12.5 into 10 to the power of 14 Hz, platinum 13.5 into 10 to the power of 14 Hz. Thus, threshold frequencies varies from metal to metal. Fourth one, maximum kinetic energy of photoelectrons is directly proportional to the frequency of incident radiation. However, it is independent of intensity of light used. Case 1. When frequency of incident light nu is less than the threshold frequency of the metal nu naught, no electron is ejected. Case 2. When frequency of incident light nu is equal to the threshold frequency of metal nu naught, photoelectrons with zero kinetic energy will be formed. Case 3. When frequency of light nu is greater than threshold frequency of metal nu naught, the photoelectrons with certain kinetic energy will be ejected. All the results observed above could not be explained on the basis of laws of classical physics. According to later, the energy content of the beam of light depends upon the brightness of the light. In other words, number of electrons ejected and kinetic energy associated with them should depend on the brightness of light. It has been observed that though the number of electrons ejected does depend upon brightness of light, the kinetic energy of the ejected electron does not. For example, red light nu equal to 4.3 to 4.6 into 10 to the power of 14 Hz of any brightness, that is intensity, may shine on a piece of potassium metal for hours, but no photoelectrons are ejected. When a very weak yellow light nu equal to 5.1 to 5.2 into 10 to the power of 14 hertz shines on the potassium metal, the photoelectric effect is observed because the threshold frequency nu naught for potassium metal is 5.0 into 10 to the power of 14 hertz. This value is the minimum threshold frequency for potassium metal to eject electrons. The reason of photoelectron ejected is the intensity of yellow light is nu equal to 5.1 to 5.2 into 10 to the power of 14 hertz. It is above the value of threshold frequency. Why photoelectric effect cannot be explained by classical physics? The photoelectric effect has three important characteristics that cannot be explained by classical physics. 1. The absence of a lag time. 2. The independence of the kinetic energy of photoelectrons and the intensity of incident radiation. Third one is the presence of a cutoff frequency. Let's see all the three one by one. 1. Absence of time lag. When electromagnetic radiation is incident on a metal surface with a frequency more than the threshold frequency, then electrons are emitted immediately from the metal surface, even for low intensity radiation. This absence of lag time contradicts classical physics understanding, in which irradiated electrons would take a significant time to gain energy before they can leave the metal surface. But such an energy buildup is not observed. 2. The independence of the kinetic energy of photoelectrons and the intensity of incident radiation. If a metal surface is exposed to the electromagnetic radiation of higher frequency, then quantum energy observed is used in two ways. 1. A part of the energy is used to free the electron from the atom. This energy is known as photoelectric work function. This is denoted by W naught. 2. The rest of energy is used in giving kinetic energy to the electron. Thus, energy of the photon h nu equal to W naught plus half mv square, where v is the velocity of the emitted electron. When the photon's energy is such that it can only liberate the electron, the kinetic energy factor becomes 0. Thus, the energy required for the ejection of electron is equal to photoelectric work function equal to Planck's constant into threshold frequency. From equation 1, kinetic energy equal to h nu minus work function. Substitute the value of W naught in the above equation. This equation is called Einstein photoelectric equation. According to this equation, kinetic energy is directly proportional to frequency. Therefore, kinetic energy depends only on the frequency and not on the intensity of radiation. Thus, the maximum kinetic energy is independent of intensity of radiation. In classical theory, the photoelectron absorbs electromagnetic energy in a continuous way. This means that when the incident radiation has a high intensity, the kinetic energy is expected to be high. Similarly, when the radiation has a low intensity, the kinetic energy is expected to be low. But the experiment shows there is no photoelectric effect in such a manner. Based on quantum theory, here the detected photocurrent plotted versus the applied potential difference shows that for any intensity of incident radiation, whether the intensity is high or low, the value of stopping potential is always the same. Thus, that the maximum kinetic energy of photoelectrons is independent of the intensity of light. Third one, the presence of a cutoff frequency. The cutoff frequency is the minimum frequency that is required for the emission of electrons from a metallic surface due to incident radiation. Below the cutoff frequency, the phenomenon of the photoelectric effect stops altogether. When electromagnetic radiation is incident upon a metallic surface, if the radiation has a frequency greater than the threshold frequency, a part of the energy of the incident radiation is absorbed by the electron on the metallic surface, facilitating electronic excitement. The remaining portion is transformed into the kinetic energy of the electrons and accounts for their ejection. Kinetic energy of photoelectrons at the surface versus the frequency of incident radiation. The photoelectric effect can only occur above the cutoff frequency. No C. Measurement for all metal surface give linear plots with one slope. Each metal surface has its own cutoff frequency. None of these observed phenomena is in accord with the classical understanding of nature. For classical understanding of nature, as long as the light is shining, the photoelectric effect is expected to continue.